Hi, good morning. Welcome, everyone. Thank you for being here today with us. I can reckon some known faces, but for whom doesn't know me, I'm Enrico BRAGAGNOLO, and I'm part of the sales team at Breton. We specialize in manufacturing and implementing machining solutions and additive solutions for the industry. So we're here today to provide you an outlook about what's our stage in solution about the large additive manufacturing with FDM systems, and what kind of solution we're ready to deliver to the industry to bridge the existing gaps that we found in the market. When we come across to additive manufacturing, of course, we'll be facing different kind of solutions, different kind of printing methods. We go from the SLS to jet bending and other techniques. Where we really focus is the FDM, so fused deposition modeling. And we focus on the large-scale FDM systems. On the FDM systems, there is a challenge nowadays to scale it to the industry on the large formats, and that's represented by the challenge to make the process becoming easier and more transparent for the operators, for the end users. So today we will see, in fact, what are the existing challenges for the operators or for the end user of those solutions. We will see what are the essential requirements for a good thermoplastic extrusion process, because this is what we're talking about, thermoplastic extrusion process. And then we will see how important it is to come to the possibility to predict the process rather than repeat failing on the different trials. I'll get you some information as well on how we came to this development and how we use the design of experiments to determine what is wrong and what is right. And then we will see together how we've been able to define an artificial intelligence and machine learning solution to bridge the existing gaps between the available platforms and the machine itself, and the, let's say, the equipment that will, at the very end, manufacture the part. I will provide you then a summary of what are, in our opinion, the benefit for the end users and for the operators, and how they can get the results guaranteed when approaching the additive manufacturing of large format FDM, and then we will come to the conclusion together. Well, what are today's the challenges for the end users of FDM? In other technologies, like in jet bending or SLS, it's everything a little bit more consolidated already, because many of us has already a small printer at home, or even on a larger scale, we have big players that made everything easy for the operators. When it was when we speak about, for instance, jet bending, we have big players that created something really easy for the end users. And the processes there are more stable, reliable, known. The knowledge is very diffuse, so that's a little bit easier. But again, doesn't matter which the technology is, there are solutions which are, let me say, out of the shelf and already done, and then we see sometime, especially on the FDM, the sector that we mostly refer to, that there are even, let me call it, garage-type solutions. So people that is trying to get something together to create a possible kind of equipment that put one layer on top of another. Well, when we look at the FDM, and I don't know how many of you has a small FDM solution at home, when we come to the FDM on the user side, on the consumer side, there is already a lot of solution available in the market. So there are softwares which help the operator or the end user to define the printing position for the part, to define supports, to understand how the process should be done, or even to determine automatically the complete process. But when it comes to large additive manufacturing, so FDM on a massively larger scale, well, when we entered this market, we found that there was not enough, let me say, not enough consolidated system to make the process easier for the operators, and that's exactly where we focus with our development. Talking about the challenges, again, we saw that most of the solutions that are now available as a software or preparation work for the FDMs, they tend to neglect all the kind of parameters which are on the other hand, essential to get to a perfect printed part. So today, there are very, very few solutions which are considering, for instance, I don't know, the fluidodynamics into the parts, or the way we get the material through a nozzle, through an extruder, or how that extruded material comes on top of the previous layer or a previous support. And then, again, even if we find something that it takes into consideration the fluids and the behavior of the fluids, that it was maybe not enough yet to get the right fluid with the right material on the right extruder. So it was enough to change one of these things in the middle and get a completely unknown environment to work with. And again, temperature on large format is a big challenge. Is maybe one of the most critical aspects that we should take care about. And again, the existing solution, they were not, in our opinion, at a sufficient level to cover the entire process with a perfect control of the temperatures. If you had any chance to speak with people that is making injection in molds, which is probably the technique which is much closer to the kind of extrusion that we're doing on large format FDMs. So everybody that is already familiar with injection in molds can confirm that one of the most important thing is to define the good parameters, the good conditions, the good set of data for the injection of the material, and to keep them stable, absolutely stable, or as much stable as possible along the complete extrusion process. Some of them, when we spoke with them, they told us never change something while you're extruding, otherwise we completely damage the part. Okay, so putting material layer on top of a layer, it's even a bit more difficult because we work on an open area which is subject to many changes, many more than what we can have on a closed mold or an injection mold. That's why we understood from the very beginning how important it was to predict the process rather than controlling the process at the very end. So predict the extrusion is something, but predict the complete process, including the extrusion, is something a step higher, a step forward, which is even more complicated, I can assure you. So how can we come to predict the behavior of the process, the complete printing method on top of layers and layers? Well, we're not wizards, we're not magicians, we cannot just guess how the things will come. So we found that is everything down to maths, algorithms, rules, formulas and recipes. So in our approach, we used practically a method which is the design of experiments to determine which are those correct parameters, the right recipes and the right formulas. We design a method to apply a good DOE, and then we made all of these because we couldn't afford to get, let me say, just a learning by making wrong things or by failing, let's say. So this design of experiment method that we develop is what has been the origin for the data that we started to collect and to feed into the calculation methods. So when we have a design of experiments and we have a result from the experiments, we cannot, for the many of experiments we can conduct, probably we will never catch all the conditions that we will then face when we are printing and manufacturing a complete part into a machine. So we immediately understood that our simple method of calculation was not enough. So a little bit like the origin of the computers, we understood that we needed to have an help from a sort of artificial intelligence that is able to simulate the behavior and calculate the behavior on thousands and thousands of different conditions. And among the different simulation and among the different conditions, an artificial intelligence which is able to choose which are the best conditions to apply at the process. So now the benefits for the operators when it comes for him to guarantee a good result is that it's a kind of difficulty to get even when you set up the parameters on the right way and you got everything already defined, is quite difficult to maintain them all along the process and to control those many aspects that are coming out of the during the process, because we are talking about flow rate, temperature, humidity, and many other aspects that are involved in the process. So for an operator is a kind of a nightmare to control all those things, even if a previous, let's say, tool, let's call it tool, a previous tool already defined which are the good ones. So we said, okay, now that we define which are the good conditions, how can we get someone to monitor that those conditions are respected and made accurate on the machine? So in the example of the predictive solution that we have on the FDM system, we can show how it was, for instance, the best estimate and calculation done by a very experienced operator. Okay, so the definition of the slicing on the part, the modification that an operator could apply on the different layers, the income on the layer and the outcome on the layers. So the best solution made by an operator, and to compare it with the best solution calculated on thousands and thousands of best assessment done automatically by an artificial intelligence system. So in our experiments and in our trials and in our demonstrations, we have been able to prove how a good artificial intelligence system is able not only to make the process more reliable and stable and affordable, but also to save material, save time, and go straight to the end of the part, which is something that is absolutely more competitive. And the AI, the artificial intelligence, is right there now to bridge the gap from the CAD-CAM system or from the existing CAD-CAM solutions and the machines. So the algorithms which are contained in a good AI system for the control of a large-scale FDM system, they are there to take the input of the CAM systems, reprocess the CAM data, make a good interpretation of them, and then modify all of them, or a good part of them, in order to pass to the machine the right parameters, the right information, and the right set of conditions to get the part at its best condition at the very end. So we said the parameters are that many in the process, so that's why, for instance, we need to control the temperature of the extruder flow rate, we need to control the axis feed rate on the machine, we need to control jerks, acceleration, radial accelerations, many other aspects. And that's why we have been called to design our own extrusion line, our own extrusion systems and nozzles and heating system and heating chambers, barrels and whatsoever, because out of the shelf from the market, we couldn't reach, or we couldn't find something at a sufficient level of development for what we found it was required by a stable process and a reliable process. That's an example of how we monitoring, controlling in the machine all the different temperature at the different stage of the screw in the extruder. We need also to control the dynamic behavior of the layers and the parts, how the parts deform under temperature, because it's not sufficient it's not enough to look at the last few layers distributed on top of the part, but we also need to keep under control the total temperature of the part, the whole of the part in its own behavior. We need to define different parameters according to the length of the path, and we do all of this because we absolutely want to avoid a process where the part is maybe almost close to collapse, or is not, on the other end, for instance, is not providing the best bonding between the different layers, the best adhesion between the different layers. So again, with our design of experiment method, we have been able to define how all those parameters need to be controlled. And something that very few are doing at the moment, but it has been something that for us has been, let me say, a game changer in all our evolutions, is the monitoring of what happened inside the flow of the extrusion. Okay, so when we extrude, for instance, materials which are composite between thermoplastics and fibers, the flow is extremely important to define where the fibers are going. And the fibers are not distributing in an even way always in any condition. So there could be so many variants in the extrusion process of a part, which brings an influence on the distribution of fiber, that it was too much for an operator, even with the best experience and the best approach, to calculate what's the best bead and what's the best condition to have a bead in the machine. So again, the predictive solution and the AI which stays behind are able to solve automatically all those questions. You can see, for instance, how we are determining the best conditions. But as you can see, for instance, we are we define a sort of protocol to measure what's the best result in printing, but as you see, we are in a fixed sample part, which is the one we use for the benchmarks and for the measurements. We have 9 areas that we can measure. Every area is divided in 10 layers, and it means that we have for every area 9 layers that we can go and check. But again, we are looking at a very limited number of possibilities, or on the best sample test that we have less than 100 different conditions that we can test and monitor. So how can we assume that those little numbers could be enough to predict any possible process coming out of any possible part? We can't do it by ourselves, so we've been forced to ask the help of a massive AI system behind, understanding which is the best condition to be applied on a brand new part that we need to run through the machine. When all those parameters are set, predicted, they go in the machine, etc., in any case, they may vary because of some unknown and unpredicted condition that comes to the machine. It's sufficient to have maybe a room change in temperature outside of the machine, or a different kind of humidity that was not foreseen before. So the machine itself, with a part of using the artificial intelligence, is using practically a feedback system that monitors all the parameters in the printing phase and brings back the information again to the AI algorithms to recalculate next time the part in a probably better way, or in a more efficient way. We collect a massive number of data during every print, and with that data, we feed back the system and the AI solution to let the system learn by doing. Okay, so we do not pretend to be the only one knowing how the thing should work and what went wrong, etc. But the machine itself and the algorithm behind can do a lot of the work for us, even using the experience that the machine is building day by day. And it's not just, in our case, it's not just linked to that specific machine, but it's a network of all our machines and all our extrusion systems that are available all around in the market, that are building, they are practically creating a larger and larger database of information, a larger database of experiences, which are then fed back to the prediction systems. So coming to a conclusion, to approach large additive manufacturing is a challenge. It's not that easy as taking an extrusion from the shelf and put it on a machine that is moving the axis up and down. It needs a perfect control of every behavior of the part, and to predict the behavior of the part during the printing process. And then we have to make it simple for the operator. We cannot we cannot force the operator to have all the years and years of experience required to be able to predict maybe the 80% of the behavior in the process. This is our Genesis solution that integrates all of these. Genesis is available on a purely additive solution. So we have a version that is basically just printing material, and then we have a second version which is combining printing, additive, with the subtractive solution, so milling, machining, and all the other kind of subtractive techniques which are a little bit more known. All right, thank you very much for listening. And if you have any question, any guess, or if you really want to investigate a little bit more into the process and into the solutions, we are here at the stand D34. Thank you, and see you next time.